Alright, I'm glad you made it to Abaqus. Welcome to our beam modeling example. We will follow the exact same steps that I presented to you in the slides. So I hope you all remember the most important thing to do at the beginning of a simulation, and I did forget this in my slides. So set work directory is the first thing you want to do. See, it's back to default. In my case, it's similar commands. Maybe in your case, it's ctemp. We want to switch back to the Abaqus tutorial 1, and yeah, we can maybe create a subfolder and go for beam modeling. Create this folder, select this as a working directory, okay, and right now we can immediately save the beam example, our CIE file, and then we'll constantly save our progress throughout the exercise. All right, so the first thing is create a part. As I said, it's a 2D planar deformable wire. So here the base feature is important. The approximate size can stay the same. And we click on continue. Now it gives us, hopefully, after some time of waiting, it gives us the option to draw what we want to have. So we can use this create connected lines option. We can now use our mouse to visually create this thing. However, we could also down here define starting and end points. So for example, we could go to 0, minus 50, then go to 0 plus 50 to get a height of 100. Then we go to 20, 50 to have the second feature point. And then we go to 100. Now you're probably quicker than I am. No, that was stupid. Damn. Okay, now the eraser might be a useful tool if you did something wrong, so you can erase this part and simply continue from here. So it should go to 150. Now it worked. Perfect. So we can click on the X or the mouse wheel to finish. So now the part should look as we've desired. Okay, so much for the parts module. That is our sketch. Now you can see if I hover the mouse over the respective parts, you see this is considered one beam. This is considered, I shouldn't say one beam, the entire thing is considered one beam. However, this is, let's say, is a section of it. Okay, now this is also confusing, but a feature section. So we could apply at this point, which is now highlighted, we could apply a boundary condition. We've talked about this before. So now let's mesh the part. As mentioned, we use the global size of 10. We can apply. We could see the seedings, and now if we mesh the part, we see, and there you can see the different nodes. And using the assign element type module, we can, if we select everything, we can then click the mouse wheel, and here in this element type window, so it was here on the left, then we selected the parts that we wanted to model or where we wanted to assign a new element type, and then the family is beam, of course, and here you see, okay, B21, a 2-node linear beam in a plane, so shear flexible. Here, checking hybrid formulation or not, cubic formulation would switch from Timoshenko, which is shear flexible, to Euler-Bernoulli. Here, quadratic, you have B22 now. So let's start with the B21, which is a Timoshenko beam with the linear geometric order. We can click on OK, click the mouse wheel, and now we have assigned the B21 element type to all of our bracket. All right, next on is the material models. Click on, double click on to create elastic and simple plastic. So for the elastic part, I said I'm using megapascal, 0.33 for the Poisson's ratio, and simple linear elastic. So we start at an initial yield stress of 250 MPa, and we go up to, let's say, 600 at a relatively large strain of 1. So isotropic hardening, for this case, this is sufficient. Okay, so now it's getting a little bit more interesting. So when we define the section, oh no, so maybe we should sorry, yeah, now remember. So for beam, you need a beam orientation, and that it's the easiest thing to do is if you go to assign on top here and then beam section orientation. Yeah, so select the regions to be assigned a beam section orientation. You have to do it for all your beams. You select the entire thing, and now it gives you, for example, an initial guess. That looks right, so it's 0, 0, minus 1. Okay, we can define enter here and click on OK. So now it would be interesting to see how the thing has applied this sort of orientation. However, for this, we first want to create a profile, and in this case, a rectangular shape. It has it's 10 by 5, as I said. Click on OK. Then we create a section, and this shall be a beam type. We didn't talk about trusses. That's also a different topic, but for now we use beams. During the analysis, before the analysis, and now we have to, other than like in the previous tutorial, you only had to choose the material if you chose the homogeneous solid, but if you use a beam section, you also have to define the profile that you just created. Same holds for the material, and you can do some more advanced stuff here, but for now it should be sufficient to just create it. And then we finally go back and assign the section. Yeah, section 1, it's a beam type, it follows material 1. It does not show you the profile that you've chosen here, so in order to make sure, check your section definition to make sure you use the right profile. All right, so now if we go to our part module, and then under view, on the very top here, you can go to view options, no, part display options, and then you can go to idealizations, and here you can check render beam profiles. So right now it only shows you, let's say, a thin line with no specific cross-section or whatever, but if you want to see and, for example, understand about your profile, then it's helpful to visualize this. And you see, okay, it makes sense. However, you see, for example, that the profile we defined, 10 by 5, is now assigned in the direct in the vertical direction, not in the parallel to the plane direction. So for example, if we go back to property and then assign beam section orientation, and now we can, since the set was created before, we can click on sets, and set 2 is the one where we define our orientation to. Maybe we switch to, let's go 0, 1, 0. And now you see the tangent is still correct, so it follows the beam axis, but the first and second orientation now is assigned in the different order. However, you see this is basically still the same as before. So maybe to highlight the effect of it, we can beam section. Okay, sorry for the confusing. It seems that in the newer version you cannot change this for 2D object anymore. So you would have to change the profile orientation. So for example, go to 5, 10 here, and then you see it's now differently oriented. It used to work in previous versions, but however, if you go for a 3D model, you can still do this. I didn't see the warning down here where it says you cannot do this for a 2-dimensional part anymore. Okay, then let's just continue. The assembly is a straightforward thing. We have one part. We can create this one instance. And the step we want to analyze is basically a static general step. And let's go to energium on. And as I pointed out, give it some more room and define a maximum step of 0.1 and an initial step of 0.01. And that should be fine now. The reactions forces we can check. So forces, yeah, reaction forces are activated. So much for this. Then we define velocities. So we use, how we call it, let's say fixed ends. And then we choose this point. And now here you can see that you can only choose these feature points that you have previously defined. So this is going to be encastered, so these stay fixed. Whereas second boundary conditions, so we call it velocity in y direction, velocity based, we apply this to this one additional feature point, and and here again it will make a huge difference if we, for example, do it like this, or alternatively, for example, allow movement in the x direction. So we can do a lot of these things and then compare what we want to compare. So let's keep it fixed in this case. Job, I will now, so what we use, it's bracket B21 type, 5 to 10 orientation, energium on, and Vx is 0. So I usually tend to include a lot of information in my job so that I can later compare it easily and remember what was going on. So we can submit it, and then we can activate the monitor and see if we did something wrong. That would appear in the errors tab. So far it looks good. Everything's fine. The status file, yeah, a lot of calculations going on. I hope that it will work and that we see a converged solution. Yeah, looks good. So this one is done now. So for example, we could, before looking at the results, we can, for example, uncheck the velocity in x direction and now create a new job. So same name, so it's B21, 5 by 10, still NMGeom on, but VX free. So, and if we now run the second job, the cool thing is that now it takes the information, as I said in the previous tutorial, of the current configuration of my model tree. So if I would now rerun the first one, I would overwrite the results. So do not do this. Keep the two as it is. And while this one is running, you could like keep going and, for example, switch the element type. What you do under mesh, assign element type. And then, for example, you could go to B23. For example, that means you would use an Euler-Bernoulli beam. And maybe we can do this as a last job. So bracket, it's now B23, 5 by 10. Still NLGeom is on. It will be also interesting to see how Euler-Bernoulli changes if you uncheck NLGeom, or how Timoshenko beam behaves. So you see there's a lot to investigate, and I highly recommend to go through all these variations and understand the effects of different element types, the effects of NLGeom, and so on and so on. So while this one is running, we can, for example, here look at the results and see, yeah, holy camoly, but still it looks as expected. One important thing to highlight here is this edge. We'll look at the how it evolves over time. You see there is always a 90 degrees angle, and this is due to the fact that we modeled, or we sketched, this part as one single part. So this is quite important to understand. So whenever you change the geometry of a part, so for example here you change from vertical to horizontal, it will, so to say, weld this connection with an infinitely stiff welding connection. So this will stay 90 degrees because you geometrically ask for it. So you would have to connect, this is more advanced topics. If you want to have like a special joint in here, you would have to model it differently. So don't get confused why this stays at 90 degrees. It does so because you're asked to. You can now also see that the elements stay straight, and this is the point where we applied. So it was a distance of 20, the length 10 per element. So it was this point to which we applied the forces. And now we want to do the same trick as I talked about the last time. We create a new viewport. In this case, we tile them vertically, and then we load a second simulation to the second viewport. And let's do a time synchronous link. So now we link the viewports again, and then if we shift and zoom, we see the same. So you can definitely see, by allowing the movement of the point to the right in horizontal direction, you can see that you allowed this vertical part of your beam structure to stay more vertical, because whereas in this case, where you forced it to remain on this vertical line, the deformation had to be reflected or depicted by this part of your beam, where in this case it was definitely moving to the right. And now we want to see how far this moved to the right, and we can, for example, use this using our XY data tool and then access our field output. Then we go to unique nodal, and then we go to spatial displacement, and then we go to U1, which is the horizontal direction. We go to elements 1, then we edit the selection. We select this point, click on the mouse wheel, and then we click on plot. And now we see, okay, this is the displacement of the feature point where we did not specify any velocity in the horizontal direction. We kept it free. And so it's interesting to see how this displacement evolves over time, for example. That is one thing you should be interested in. So you can verify your boundary conditions. Yep, it's exactly 0 because we asked it to stay at 0. And as another thing, I want to now show you how we can combine two XY data sets. So we'll now take the U2 displacement and the reaction force in the vertical direction of the feature point. So this one, at selection, one node is selected. Yes, we can plot it. Yeah. So we see the two values over time, but it would be interesting to display the force over displacement, not over time. So even though in this case the displacement is linear, you can say, yes, Josh, why you're doing this? It's just that in some other cases your movement might be non-linear, so it's not the same plotting it against the time or the displacement. So we click on dismiss, and then we find the XY data here. We have the reference, the reaction force 2 and U2, and then we can say, okay, XY data. We can click on operate on XY data. We click OK. Then we scroll down to find combine here, and then we say reference versus, reaction force versus displacement, and then we can plot this expression, and then you say, yep, he did it wrong, so the other way around. Okay. Here you see it's a good effect that I did this mistake. If you do not save the XY data, but you combine it, the original data is lost. So that's a pain in the ass. So in this case, you would have to go back and get the data again. Yes. So plot, now we have the data again. We could now save this and save this also, so this isn't lost when we do a combining operation on these two data sets. I don't know why Abaqus is still doing this. You could give it a different name, but it keeps the information. So it's U2 versus reaction force, and now you can see it. So this is what we wanted to have, force versus displacement diagram. You could, now it goes from 0 here to minus. You could also operate on the data just to invert the value, just multiply it by -1, and you can read the graph from the left to the right. But it's just interesting to see how this evolves over time. So in the beginning, there seems to be like a very steep increase of the force versus only a small fraction of displacement. And later on, it goes to a linear. But you can definitely see some nonlinear effects in this area here. And you should definitely uncheck NLGeom and see how in this area, for example, the force displacement diagram changes. So if we keep if we do not force the movement of our feature point, then let's see what happens. If we plot the combine, and now it's this one versus this one, and then we can plot the expression. And you see this looks vastly different to the one on the left. Especially the amplitude is different, and it does not also, the amplitude does not increase over time, because now the horizontal part, so to say, gives way, so it's weaker than the vertical part, so you need less force to continue the deflection of this beam. So yeah, play a lot, so play around outside, but also sometimes inside using Abaqus. Take a look at the different analysis aspects that I also pointed out, nonlinear geometry, different element types, and so on and so on. I hope I presented you the basics of the beam modeling. The beam section orientation thing, yes, there was a problem in 2D. If you go to 3D, this will definitely work. And yeah, stay tuned. See ya.